Okay, so for today, there's no lab due this week, so woo. So you don't have to deal with that this week. I'm just gonna basically go over references. Um, Actually, not references. I'm going over like the stack and heap stuff like that today, um, and kind of get you familiar with that. I think that's what you guys have done in lecture these past 2 days. Um, so I'm going to go ahead and touch on that, and I think that's what your quiz is on a little bit, dynamic memory, and that'll be due I think today. We can go ahead and get started, and I'll just share my screen. You guys see this? Okay. Cool. Okay, so the first thing I'm going to kind of go over is basically like the model, how we view the stack and the heap. So let me go ahead and draw on the screen. I'm going to be doing a decent amount of drawings today, so just kind of bear with that. Can be a little tedious. Uh, so a lot of times what we'll see is that we have the stack growing down like this, um, and then we have the heap growing up towards the stack, um, and you can kind of think of this as like the zero like memory address. The very well could be zero up here. I'm not entirely sure, but basically one way or the other, this is going to be addressed incrementally. So this one would be like the top of like all your addresses, right? Um, that's supposed to say top. That's real bad. And basically what you'll find here is that the stack grows down like this, and the heap is going to grow up like this. Um, so this is the heap, and then this is the stack. So I'll kind of keep these up through these demos. Um, and basically, there's at different points during the code, some things go on the stack and some things go on the heap, right? So the first thing I want to talk about is that all variable names ever are always going to go on the stack. Whether the new keyword is associated with that variable name, it will go on to the stack. If the new keyword is used, the memory associated with that variable, so the data associated with that variable, is going to go onto the heap. Um, so basically, you can see here that yeah, on 42 and 43, we have X and Y. The new keyword isn't used here at all, and both variables are going to go onto the stack. So let's go ahead and do this. So like the X variable is going to be here, and the like Y variable is going to be on the stack. In reality, let's actually do this. In reality, like I said, because it's growing down, they're actually going to be kind of at the bottom of the stack here. And the data associated with these are also going to be like on the stack itself. So the variable name and the data are going to be like associated with the stack. And then we'll go over the heap in a second. A lot of things that we'll talk about today has to do with when you make new memory, you need to delete memory, and you need a pointer to point at new memory. So one thing I want to make clear though, the relationship here is that um, some people, once they learn about dynamic memory, they start to assume anytime there's a pointer, there must be some delete associated with it because it's a pointer, so we need to delete whatever memory it's pointing to, right? Um, but that's not the case. If there is no new keyword, there's no reason for delete. So for instance, in this example right here, where I basically just have two different variables and I have a pointer that points to X and I have a pointer, the same pointer then changes and points to Y. Nowhere in there are we like leaking memory. It is just all on the stack, and the stack doesn't leak memory. It's not new dynamic memory. So there's no reason to delete this pointer. Where some people assume that because there's a pointer, you need to delete it. So the relationship is basically all dynamic memory requires a pointer, and you'll need new and deletes, but not every time you have a pointer do you need to call deletes or new. So that's kind of the way those two things work. So there's no real, this doesn't really do anything running it. So we can kind of go to here, which is where we'll start talking about the heap itself. Um, so you can see a couple new and deletes here. So basically, anytime a new keyword happens, we are putting something onto the heap. So for line 47, we do int pointer2 equals new integer, right? And if you remember what I said, well, let's go ahead and erase these, that all data or all variable names rather are going to go on the stack no matter what. So pointer2, even though there is a new keyword associated with it, the variable name itself is going to go onto the stack. Let's get a different color. So pointer, we'll do pointer2, is on the stack. The data that is new that pointer2 is pointing to is going to be on the heap. So the actual like data there will be created on the heap, and we'll basically just get a new integer. So basically, we've created space to store an integer on the stack. So once we change pointer two to 20 right here on line 48, what you're going to see is that this will now store 20 inside of here. And that is kind of the relationship between the stack and the heap. So pointer2 itself, like the variable on the stack, right? Data it's pointing to on the heap. And this is why we need a pointer, because we can't have variable names on the heap. And we want to name our data somehow, right? But if it's going to be on the heap, how do we name it? If the heap can't have variable names, we need to put it on the stack. And you don't deal with that. It's basically the system doing that, right? When you type in line 47, this is what's going on in the background. So this is kind of the relationship that's important to kind of conceptualize and understand when you start making a bunch of new objects and deleting them and changing pointers, pointing from one way or the other, right? Any questions right now on this relationship? All right, cool. So let's see here. The next thing we'll talk about is kind of how memory leaks occur, because that's one of the biggest topics when dealing with this dynamic memory with stacks and heaps, right? So if we move along to line 50, what we'll find is we're doing pointer2 is equal to a new int. So right now pointer2 is pointing to this location on the heap, but once we make a new integer, what is happening is that we have basically created new space onto the heap. And we're now telling the pointer2 that it is no longer pointing to the 20 it was originally pointing at, and it's actually pointing to this new location, which makes a new integer, and then we set that to 15, like this, which is totally legal. It's going to let you do this, but we run into a pretty big issue, which is going to be a memory leak. So what do we mean by when we say memory leak? Basically, when this program terminates, this memory is still being used up in like the computer, which means that the application is terminated, and that is memory, or it usually maps to RAM, so random access memory for those of you familiar. And it's using some of that, and now the user can't get it back. So if they, let's say every time they boot up your application, it puts like a gigabyte of information on the heap, and they close it out, that gigabyte is still going to be on the heap. And they open up your program again, and then they close it out. Now they got 2 gigabytes. Even though the program has terminated, it's done running, their computer still has memory reserved for it. You do that a couple more times, and your computer is going to end up crashing, right? Because you've run out of memory. Now, modern day operating systems will kind of handle this, and they'll recognize that there's an issue there. But when you're developing your own application, you shouldn't make any assumptions on the environment that it's running in. And your application should be completely self-contained, meaning you should have the responsibility of dealing with these memory leaks, right? You shouldn't pass that responsibility on to the operating system. So hopefully that was clear and made sense. So looping back to how this memory leak actually occurs is we've essentially, once we've moved this pointer to somewhere else, we have completely lost access to this 20. We now have no way of referring back to that 20 and actually being able to delete it. Because you see here, once this is pointing somewhere else, we have no reference to this 20. It just doesn't exist. There's no variable name. There's no way to get back to it once we've moved that pointer. Obviously, you can change the code, but I'm strictly speaking in runtime. There's no code we could add down here that would allow us to get it back, right? So that's pretty critical. And yeah, so basically, the way to fix this is to delete the memory before you're moving the pointer. So let's say we truly wanted to do line 50, and we don't care about this 20 variable anymore. We would have to actually like delete it before we move the pointer. But let me go ahead. I got a little ahead of myself. Let me go ahead and actually run this code. And I'm running the output file through a program called Valgrind. And what Valgrind allows the user to do is actually check the memory that's been leaked in the system. And it'll actually give you like how many bytes and how many like deletes versus new that actually have occurred in the system. So if you're on like Ubuntu or Mac, you can just like install Valgrind. If you're on Windows, if you have the Windows subsystem for Linux, I think you can get the Valgrind. I was doing that in the past. If you don't have Windows subsystem for Linux, I don't know how the install process works for Valgrind. So I'll kind of leave that up to you to figure out, I guess. But yeah, basically Valgrind is the application. I'm passing in the name of the output file, so not the source file, but the actual output file that we've compiled. And then I'm just running leak check full, which basically just gives me all the details of the leak itself. So let's go ahead and run this. And what we'll find here based off of what this code is doing, just 47 through 52, what we'll find here is that the heap summary in use at exit is 4 bytes and 1 block. So this means when my application actually terminated, I'm still using 4 bytes that's on the heap. So in this machine, each integer is 4 bytes. So that makes sense. I've made one integer that I haven't deleted. This one right here has been deleted, but this one hasn't. When we went ahead and changed where the pointer was pointing to, this is the integer it's talking about, right? And what you can see is we have 3 allocates, which is like C language, but that's news, like new, the new keyword, and then 2 frees meaning delete. So a little bit different syntax and keywords there, but they mean the same thing. I think from what I understand, as you can see, it says 3 allocates, but we can clearly see there's only 2 news. I think there's like 1 allocate going on in the background for just the application itself, but don't quote me on that. But there always seems to be just 1 bonus allocate sometimes. So the key thing here is that we can see that this is not net zero. And as Fox talked about, if you have as many news as you have, you need that many deletes. And we can see that that's not the case here. When we go to the leak summary, like what we've actually leaked, it says definitely lost, and it's 4 bytes in 1 block, which makes sense again because 4 bytes is 2 ints, or 1 int rather. If we go ahead and do this again, where we can like make another new integer that we didn't delete, and we go ahead and run this, what you'll see is it's should become 8 bytes. Yeah, so 8 bytes in 2 blocks. We have 4 allocates now and only 2 frees, and delete summary is 8 bytes. Meaning now we've done, we have 3 things here on the heap, and we only have deleted 1 of them, right? So does that make sense to everybody? And if not, what are your questions? Okay. So how do we fix this? We basically just need to delete it. So if we go ahead and comment this back in, now what is occurring in the system, if we take a few steps back here, well, there goes the heap. So we take a few steps back. Sorry, this is so tedious. This was pointing here. Basically what happens when we go down here to line 49 and we call delete pointer 2, this is something that a lot of students get a little confused about because their assumption is that we're like deleting the pointer 2 variable, like we're just completely nuking the variable itself and the data that it is pointing to. In actuality, what it's truly doing is deleting the memory that it is pointing to, not the variable name itself. So pointer2 as a variable name is very much alive and well. We are just deleting the memory that it is currently pointing to. I think C did a better naming convention. They named it free. So you're freeing pointer2 as opposed to deleting pointer2. But that's just something you'll have to think about when you're typing it. Is it's not, we're not deleting the variable name. We're deleting what pointer2 is pointing to, right? We're deleting what the pointer is pointing to. So when we go ahead and do this, basically now the system knows that it can write to this location. Like this has completely been freed. It's able to actually write to this location later on in memory, right? And then if we go ahead and do this, so now on line 50, pointer2 is no longer pointing here, and we've moved it to point to this location right here. And now because of this, we won't end up with a memory leak because this location has been properly freed up. And then as we go down here, it makes a new int, sets this to 15. And then at the end, of course, we need to delete this 15, or we're still going to get a memory leak. And I can show that in a second. But for this one, everything should be fixed now. And you can see this is the way the good news looks. At exit, we're using 0 bytes and 0 blocks. We have 3 allocates and 3 frees. So that's a net 0. And then all heap blocks were freed. No leaks are possible, which is what we expect. And just to prove to you guys on 52, if we comment this out, that it doesn't just have to be with the fact that a pointer is no longer pointing to it. If we don't delete this, then that's also going to be a memory leak. If we don't delete the data that's at 15, this is also going to end up with a memory leak, as we can see. Any questions on this? Okay, cool. So let's go ahead and move on to, go ahead and do this. See if I can move this. Cool. So the next thing I'm going to show is basically what new dynamic memory like means within the system, to give you kind of some like real world perspective of like what you're doing to the computer. So here I have a for loop that is basically looping through however many times this is. I just added a bunch of zeros. I didn't really count. And it's making a new int every time it goes through this for loop. So again, if you remember, each time a new int is made, it's going to put it on the heap. And remember, I talked about the heap actually corresponding to the RAM in your computer. For those of you who are familiar, random access memory. So I can go ahead and show kind of what's going on with my system. Right now, I have 6 gigabytes using out of the 15 of my memory, which is, again, the random access memory. And what you'll see if we run this application, if you watch this dial right here, when we run this application, because it's just making a bunch of new integers, it's going to just ramp up the usage of my RAM. And basically each integer is like 4 bytes, so it's going to go up pretty quickly because these for loops are pretty fast at doing what they're supposed to do. So let's go ahead and run this. I'll run it a few times, and I'm also going to have to close out of this before it crashes my computer. So just pay attention to this little dial. That's the one that you're going to want to look at because it's pretty neat. And let's go ahead and run this without vowel grind on it. So you can see 7, 8, 9, 10, 11, 12, and then I'm going to close out of it. And as soon as I close out of it, it immediately drops down to 6. Again, this is the OS taking care of it. I didn't do any deletes here. So as you can imagine, if the OS didn't take care of that, all of that would still be sitting there like on the heap because I didn't free any of this up. So that's important to note. I didn't try this on my last lab. Let's see what this does. If we like immediately delete pointer2, what I'm expecting here is that basically this won't change at all, which hopefully shows you the relationship between the news and the deletes. Yeah, so now this isn't changing at all because we're just basically putting something on the heap, taking it off, taking off pretty much immediately. So Does that make sense to everybody? What's going on there? I can run this one more time just so we can get a better look at it. Cool. So 7, 9, 10. That one's going up pretty quick. 11. Close out of that. So that's kind of what's going on in the background of your system. So if for whatever reason you're making this much new, which I highly recommend not to, you got to keep the user's machine in the back of your mind, right? Like how much RAM do these people actually have? So cool. Let's go ahead and move this over. All right, and then I only have like one more kind of example. Today's a lot shorter than last week with all the pointers. A little bit less to go over here. This is, let's see which one I want to do. I just have a class here. I basically just wanted to show you kind of how this works with classes. A lot of times you're not making a new integer. You're not really putting new ints or characters or strings on the heap. Most of the time what you're doing is creating new objects. That's going to be the highest use case for these, the heap and dynamic memory. So let's go ahead and clean up our stack and heap real quick. Okay. So what we're going to do is we have two classes that are going to go on to the heap, and actually two objects. Not really. It's called my class, but they're two objects, right? Because they're actually instantiated. And again, if we remember, pointer 1, pointer 2, the variable names themselves are always going to go on the stack, even though they are new memory. The variable name themselves will go here. So this is pointer 1 and pointer 2. And then we actually create the memory on the heap. So this is going to be my class like 1 and then my class 2. And pointer 1 points all the way down here. Took a little detour there. There we go. And basically, if you're wondering what data is actually created here for the class, it's going to be all of this. So it's going to be enough for an integer and enough for a string. And then also, like if it had any like functions or any other, basically everything within the class, it's going to make that much room for, right? So on line 15, I went ahead and just set the integer equal to 10 so we can set some data. And then I go ahead and just print out that data to show it. And then I'm going to delete pointer 1, and then pointer 1 is going to be a null pointer, which is something I haven't touched on, but I believe Fox did. So basically, the smartest move is anytime you delete something, you're going to want to set it to a null pointer. And what this gives us the ability to do is basically not leave like a dangling pointer or a pointer pointing to memory that has already been freed. Because later we might accidentally try to access that memory, and that memory might no longer belong to that object, and you're going to get some random memory, right? Or if the application sees that you've freed up this memory, let's say when we deleted pointer 1, and then later on, if we never set this to a null pointer, later on, let's say you add a new object, and that new object somehow goes here because that memory has been freed up, and it could totally do that. Then your pointer 1 would be pointing to an object that you're not really expecting it to point to, and you can run into some really weird bugs with your application that is going to give you a headache on trying to figure out. So the smartest thing to do is when you go ahead and nuke the data that a pointer is pointing to, if you go ahead and set that data, or excuse me, that pointer rather, to a null pointer, then you won't run into that issue because it's basically pointing to nothing. It's pointing to void. It's pointing to a null pointer. One thing that you'll recognize out of this when it's pointing to a null pointer is if you attempt to access the data like this, my int, this looks totally reasonable. This looks, legal. So we're deleting this pointer, and then this pointer 1, we're just trying to get the int out of that pointer again, right? But if you remember, we just deleted it, so now it's a null pointer, and null pointer doesn't actually have an integer associated with it, right? So this is when you'll run into a memory leak, if I could type my class right. Okay. Okay, so what you should be running into once I get this to work is basically a segmentation fault because because basically now what we're trying to do is we're trying to access like my int, but it's a null pointer. Null pointer isn't an object; it's nothing. So when you try to access something from nothing, it's going to give you an error because it has no idea what to do with this. It's not going to tell you that null pointer doesn't have type my int. It's just going to kind of crash on you. So it's always something to keep in the back of your head. Basically, if you set this to a null pointer, don't try to access anything from it. Okay. So now that this is set to a null pointer, what we can do is actually move pointer 1 to point to pointer 2. If this is just what the system's doing for this example. And this is basically to show you that you can have 2 pointers pointing to the same piece of memory on the heap. And just like any other pointer in the system, you can now reference this class or this object rather with either pointer. So if we go ahead and set pointer 1 equal to pointer 2, now they're pointing at the same thing, we can call delete on pointer 1, and that's going to go ahead and actually delete what's at pointer 2 because it's the same object. And we're going to end up with like no memory leaks, which is what we expect and want. Cool. So 0 bytes and 0 blocks, 4 allocates and 4 frees. One thing that you might run into the issue, some people might think, okay, we deleted like pointer 1, and then now do we have to delete pointer 2? The answer is no, but if you go ahead and try that, you're going to get like a double free, and basically it's going to complain and yell at you that you're trying to free up something that's like already been freed. And this is kind of the issue you're going to run into. I'm basically showing you a few issues, so when you guys run into those inevitably, you will actually know like what they are and kind of what they mean, because they don't really give you a lot of context here. It just kind of like, crashes out on you. Okay, so that's that. And then very easily, you could also just do pointer 2. Obviously, what this is doing here is incredibly trivial, but it's mainly to prove a couple points to you guys. So if we go ahead and delete pointer 2, it's going to do the same thing if I run it through Valgrind, where you're going to get 0 bytes and 0 blocks and everything's freed up. So that's pretty much all I had for you guys. This one was a relatively quick one today, so hopefully this was helpful. Feel free to stick around like always to ask any questions you guys have on this or anything else. Enjoy your week off of no actual lab to do. Yeah, no problem, Mark. So yeah, and then I can go over your quizzes or whatever you guys got. So let's see. Stop sharing.